Okay, so this is a video where we're going to talk about the 3 different types of intermolecular forces. So, I'm going to actually probably start you with, we'll talk about the definition. So, an intermolecular force is also known as van der Waals forces. It's an attraction between molecules. So this only happens when you have a liquid or a solid. They're not true bonds. Bonds would be intramolecular, and those are much stronger than these. But these still do have an effect on properties of different compounds. So we're going to talk about, there's 3 different types of intermolecular forces. Here's the 3 types. So we also call them IMFs. The first one is LDF, London dispersion forces. This is the weakest of the 3, but these can become significant, and we'll talk about that if the molecule gets large enough. Then we've got dipole-dipole forces, which happens when we have a polar molecule. And then hydrogen bonds, even though they say bond, remember they're not. I don't know why we do that to you guys, but the hydrogen bond is really a special extreme case of dipole-dipole. So I'm going to show you a sim that really explains this better than I can. So let me start with London dispersion forces. So this is representing like a diatomic molecule like hydrogen or chlorine. And what we're going to see here is at any given moment, the electrons can kind of congregate on one end or the other of the molecule, giving it a temporary dipole. You can see that delta, lowercase delta positive and delta negative are partial charges. So they're, all of the electrons might kind of run to one end and away from the other end of the molecule, and then it'll just quickly shift. So these are temporary dipoles. That's why they're weaker. But the bigger and more electrons there are, the more significant this is. So right there, the gray dashed lines, that is the intermolecular force that we're talking about. And this is for the dipole-dipole. So that's a temporary dipole. So they quickly switch, and then all of a sudden the other end is the opposite charge. Dipole-dipole now is going to be stronger because this is for polar molecules. So they're permanently negative, partially negative, and partially positive. So you can see here the gray dashes are the intermolecular forces. And they can be broken. Like if you were going to, like this would be probably a liquid, you could see that they get broken and reformed, but they're still stronger because they're not shifting which end of the molecule is negative or positive. So anytime you have to boil or evaporate a liquid, you would have to break all these IMFs. So that's going to lead us down later on. And then we have hydrogen bonding, which is just a special case of dipole-dipole. These are exceptionally strong and extreme because we're talking about hydrogen, which only has 1 electron, being bonded to either oxygen, fluorine, or nitrogen. And those are the most electronegative elements on the periodic table. So they are just really extreme cases of the high electronegative element pulling on hydrogen's only electron, which exposes the nucleus and makes it so that their dipoles, their partial positives and partial negative part of the molecule is just more extreme than it is for just a plain normal. It's still a polar molecule, but it's just an extreme case. So this is representing hydrogen bonding. And again, those hydrogen bonds are formed and, broken and reformed continually in a liquid. All of those IMFs have to be broken, like in order to go to boil or to evaporate for them to escape. So we're going to talk about that in just a second. So let's just talk about each one at a time. So LDF, London dispersion forces, every molecule has these. They all have electrons that can temporarily go to one side of the molecule and away from the other side, which creates a partial negative on the side where the electrons are moving, partial positive where they came from. And the 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 dipoles themselves, the polarity, the electrons moving to one side or the other, are temporary. So temporary dipole, but the attraction is still always between one molecule's negative side and then the other molecule's positive side. And these get stronger, like I said, I think I said this already, as the molar mass increases, which is the mass of the molecule, it means that you're going to have more electrons. Dipole-dipole is when you have polar molecules. That's the key here. So they're not temporary dipoles, they're permanent dipoles. So again, in this slide, the dotted lines are representing the dipole-dipole interaction. So if you have equal sized molecules, the dipole-dipole is going to be stronger than the LDF. And then lastly, our hydrogen bond, it has to be a hydrogen directly bonded to, I call that NOF, nitrogen, oxygen, or fluorine, and it has to be a polar molecule. And then it can have hydrogen bonding. So it's just a stronger dipole-dipole. And it's possible to have, I can't think of an example. It's possible to have hydrogen directly bonded to NOF, N or F, and to be a nonpolar molecule. Then it wouldn't have hydrogen bonding. It would only have LDF. So properties of covalent compounds. So we know, and I've been saying this, in order to boil something or evaporate, the IMFs of the liquid have to be broken. So the weaker those IMFs, the easier it is to break them, and the easier it's going to have of evaporating or melting. Also, you have to break the IMFs to turn into a liquid. So the stronger the IMFs, the less likely they're going to evaporate or boil or melt. And the weaker they are, the more likely that you can break them. So solubility of polar molecules, ionic compounds are soluble in water. So on the bottom left here, the water itself is polar. So it'll surround the cation, the anions, with the side of the water molecule that has the opposite charge. But polar molecules are also sometimes soluble in water. They're not ions, so there's still not going to be an electrolyte. But if the molecule has polarity, and it's not too large, they can be water soluble because of that. So this is something just kind of being able to look now at a molecule and to say what kind of IMF it has. This is a flowchart that you can use to help you kind of reason through it. So the first thing you always have to look at is the molecule polar? If it's not, then it's only going to have London dispersion forces. If it is polar, then you have to decide, does it have a hydrogen bond? And so if it has hydrogen with nitrogen, oxygen, or fluorine, then it's going to have a hydrogen bond IMF. And if it doesn't have hydrogen with NORF, then it's going to have a dipole-dipole. So if we look at this worksheet and we add a column, it wasn't here, but let's look at a couple here. So this first one, this molecule is polar. Remember, trig pyramids are always polar. And it does have a hydrogen bonded directly to nitrogen. So this is going to have H bond IMFs. Next one, remember trig planar, they're all the same element. It's going to be nonpolar, so this is only going to have LDF, London dispersion. Next one, this is polar, and there's no hydrogen bonded directly to NOF, so this is going to be dipole-dipole. So that's kind of how you have to look at the elements, the molecules, sorry. So you have to determine the polarity. If it's nonpolar, it's only LDF. If it's polar, it's either dipole-dipole or H bond. So looking at some of the physical properties of molecules, like if you look at chlorine on here, has a boiling, is this boiling? Yeah, boiling point of negative or 59, sorry, positive 59. Chlorine is negative 34. So bromine has a higher boiling point, which means it has stronger IMFs because it's harder to break them. And why is that? They're both going to have only LDF because if you draw them out, they're just, completely nonpolar molecules. But the bromine is much bigger. So the bromine has more electrons. It has, 30, about 70 electrons for the two of them, versus the chlorine has about 34 electrons. So it has like double the electrons. So then when it does form those temporary dipoles, they're going to be stronger. And that is why the boiling point is higher for the bromine. Next, we're going to look at two similar compounds again. So if I have iodine directly bonded to chlorine, you can tell that's going to be a polar molecule, and it's going to have dipole-dipole. This one is nonpolar, it's going to have LDF. So this one should have a higher boiling point. And if we look here, it is 97 versus the chlorine is negative 34. So much higher, about almost like 130 degrees higher because of this having dipole-dipole, which are stronger IMFs than just the London dispersion forces here. And then if you want to compare hydrogen bonding to dipole-dipole, water has a boiling point of 100. And remember, water is polar, and it is going to have H bonding because it's got hydrogen bonded to oxygen. H2S is also a bent shape, so it's polar, but it's not a H bond, so it's only going to have dipole-dipole interactions. And then if we look at them, the H2S has a boiling of negative 60. Wait, let me look. Negative 61 Celsius. So almost 160 degree difference, or over 160 degree difference. So the water doesn't boil at that low temperature like the H2S does because the IMFs between the water molecules are much stronger because it has hydrogen bonding.